Okay, welcome to this week's first lecture. As you know, I've told you that I'm going to actually record 2 lectures in this week because I have already exceeded my time last week. And in this lecture, in this first lecture, we're going to see the rotational systems. Remember, so far in mathematical modeling, we have seen electric circuits and translational mechanical systems. As a second type of mechanical system, we're going to see rotational mechanical system. And if you understand translational mechanical systems, it is just a translation of all of the variables into rotational variable. In this case, the force in translational mechanical system will turn into a torque in rotational system, and displacement, linear displacement in translational mechanical system will turn into just angular displacement in rotational mechanical system. So if you make this analogy between these 2 worlds, then you're going to understand everything quite easily. So the next topic after rotational mechanical systems will be the DC motor in our modeling part, and that is going to connect the electrical world with the mechanical world. So electric motor is making a connection between an electric circuit and the mechanical system through the rotational systems actually. But before we start with the DC motor, we are going to manage some block diagrams. So the topic of this first lecture is going to be rotational mechanical systems and managing or handling the block diagrams. But first we have rotational mechanical systems. So as in all modeling part, I will start with the components of rotational mechanical systems that we will consider. So in translational mechanical systems, we have mass as the first element, and in rotational mechanical systems, we will have something called inertia, and we will show the moment of inertia with J. So this is the representation of an inertia. We are going to be applying a torque to this inertia from outside, and we are going to be getting a displacement, which is the angular displacement by theta. And so I need to write here inertia. So what is the relationship? What is the terminal equation for an inertia? In this case, remember what it was for the mass in translational mechanical systems. Remember, the relationship was F equals to m times x double dot. And in this case, force turns into a torque, and x turns into theta, angular displacement. And as a result, the terminal equation for an inertia is given as J times theta double dot. So theta is angular displacement, theta dot is angular velocity, and theta double dot is the angular acceleration. So we have here mass, it is inertia, times the angular acceleration is going to give us the torque. Or the angular displacement that we will get from the inertia will be related to the torque with such an equation. The second component is rotational spring. In this case, the depiction is going to be something very close to what we have for a translational spring. In this case, instead of pulling or pushing the spring, we are going to be rotating the spring in rotational motion. And we have again a spring constant K here, and again we apply a torque and we get a displacement, angular displacement from the spring. And what is the relationship? Remember the translational mechanical systems, in that case we have force equals to K times the displacement. Here we have torque equals to K times the angular displacement. Okay? So the displacement of theta and the torque is linearly related. And as a third element, we have a rotational damper. Remember, damper in translational mechanical system is representing friction. Here it has a similar purpose, and its notation is looking like this. Almost, it is the same as a translational damper. In this case, we again have a fluid, and in that fluid, we are rotating a propeller. Okay? So a rotational damper. You can think of it as a propeller we are rotating in a thick liquid like honey, which was my example last time. So there's tau and theta here. Remember, what was the equation relating the force and the displacement in translational mechanical systems? It was force equals to B times x dot. And here we have again a friction constant B here, and we have force, which is torque in this case. It's B times, instead of x dot, I have theta dot here. And this again represents the energy loss or friction in rotational systems. Remember, in translational mechanical systems, we had a device that is converting x's and the forces linearly into each other on both sides. It was lever. It is an energy conversion device or power conversion device. You can call it like that. And in the rotational systems, we have also its equivalent. And in this case, it is called a gear. So a gear is shown like this. Of course, it has some cogs here. These are çark in Turkish. So there are some teeth here that these gears are turning with. And when I apply a force or when I apply a torque on one side, I get a torque applied to the outside from the second side. Okay? So here we have the radii here, which is R1 and R2 here. And I apply a torque here, it's tau 1, or we apply an angular displacement from this side, it is theta 1. And when I apply a torque, the second gear here is applying another torque to the outside world. And its direction is given like this. This is tau 2, or it may be an angular displacement on the other side, which is theta 2. Okay? So our gear is like this, and I need to write the equations turning tau 1 into tau 2 and theta 1 into theta 2. Okay? So in this picture, I have drawn R2 to be larger. Okay? Now I have to think about how to write these equations. I know that there is going to be a constant multiplier here in front of both of these variables here, and it is easier for me usually to think about this constant here. All right? Think about if I turn the first gear, the gear on the left, with angle theta 1, what is going to be the angle that the second gear is rotating with? If I turn the first gear with angle theta 1, what is going to be the angle that the second gear is turning with? Is it going to be a smaller angle than theta 1 or a larger than theta 1? Because the radius of the second gear is larger, when I turn the smaller gear with an angle theta 1, theta 2 is going to be actually smaller. All right? Therefore, here the coefficient that I have to put here is going to be R1 over R2. And R1 over R2, because R2 is larger here, this is going to be a constant smaller than 1. Okay? And as a result, theta 2 is going to be smaller than theta 1. All right? If R2 is smaller, then this constant is going to be larger than 1. And in that case, theta 2 is going to be larger than theta 1. And you might remember that when I write one of these coefficients, the second one is always easier because it's going to be the reverse of this first coefficient. This is because of the conservation of energy or power, you might say. So here, if this coefficient is R1 over R2, then this is going to be R2 over R1. Because when I multiply tau 2 and theta 2 and with tau 1 and theta 1, these two numbers should be equal. So these coefficients should cancel actually each other. So these are the equations of the gear that we are going to use. Remember, try to choose yourself which one would you prefer to put first. Which coefficient would you prefer to write first, and the other one is going to be the reverse of the first one. So these are the terminal equations, and we use again the Newton's law. We use Newton's law to obtain the mathematical models. All right? And what is Newton's law in this case? So inertia times angular acceleration. Inertia times theta double dot is going to be equal to the net torque applied onto the inertia from the outside in the direction of increasing theta here. So this is the Newton's second law written in angular coordinates. Okay, so this is like m times acceleration is equal to net force. All right, it is the equivalent of Newton's second law in rotational systems. So now let us immediately solve an example. So our example contains a gear like this, and here I'm writing N1, N2. These are the same as R1 and R2. Sometimes we show it with the capital letters N. And I have an inertia here. This is J, and I have some friction with coefficient B, and I have a spring connected to here, which is K. All right, this is inertia J, and I'm calling these some variables here. This is theta 1, or showing it as tau 1. A torque is applied, or a displacement theta 1 is applied. And the corresponding displacement and torque that we get from this side they are called tau 2 and theta 2. Okay? And here, of course, I need to define what the input is. Input is tau 1. So the torque I apply on this side is the input, and the output is theta 1. The displacement that I get, I apply a torque and I look at the displacement that I get from the gear, and that is going to be the output, theta 1. So sometimes we show friction in this way, or sometimes we might show it also like this. Okay, these are the same things. So this is my J. Sometimes we show the friction with this and this, like this. These are showing the same thing. So this is K and this is B here. Sometimes instead of showing the friction in this manner, we show it like this, connecting the inertia to a damper in addition to this spring here. So these are equivalent to each other. And the task here that we have to do is find differential equation, transfer function, and state space representations. A mathematical modeling task. So we are given the system, the actual system, and what we have to do is to find its representations in mathematical world. And we have seen so far 3 representations: differential equation representation, transfer function representation in Laplace domain, and state space representation with a state vector x. So now we always start such problems by writing J times. It is It is angular displacement double dot. It's angular acceleration. So we see that the angular displacement of this inertia is theta 2. It's on this side of the gear. So this is going to be theta 2 double dot. Okay? This is going to be equal to the net torque applied on the right-hand side. Okay? I'm going to put here the net torque applied onto this inertia on the right hand side. Okay, so I know that if we are applying tau 1 from the left here, tau 2, the gear is applying a torque onto J, and it's in the same direction as theta 2. So the first torque that I'm going to put here is going to be the external torque coming from the gear. The second torque is going to be related to this B. Okay, I will put a minus sign B, and then I will write the friction force here, B times theta 2 dot here. Okay, this is going to be my friction torque that is going to be applied, and there is a minus sign as you see here. And finally, the torque applied by the spring onto the inertia is going to be minus K times, it is going to be theta 2. If you have an inertia like this, theta 2, the displacement is here and here would be the same. Okay? This is a rigid body, and displacement on one side is going to be equal to the displacement on the other side. That is why here the displacement of the spring is going to be theta 2 as well, times K is going to be the opposing force onto the motion of this inertia, and I put the opposing sign here, which is a negative sign, to include the torque which is applied onto the inertia by the outside sources. Okay? So this is my differential equation, but as you see here, these variables are not really related to the input or the output. Okay, so I have the input theta 1 here, I have theta 2 here in the differential equation. And similarly, I have the output theta 1, and this differential equation is related to theta 2. And I have the input tau 1, differential equation is related to the torque tau 2. Now I'm going to be writing the equations describing the relationship tau 1 and tau 2 and theta 2 to tau 1 and theta 1. Let us write those. So I have tau 1 here and tau 2 here, and theta 2 here and theta 1 here. So I'm going to put here n1 over n2. That is the coefficient which is smaller than 1, which is going to make theta 2 smaller than theta 1, which is what I see here from these gears. And finally, I have here n2 over n1 as the reverse coefficient. Okay? Now, in order to complete the differential equation representation, I need to convert these variables, theta 2 to theta 1 and tau 2 to tau 1. The first thing I am going to be doing is replacing this tau 2 with this tau 1 term. So it's going to be j times theta 2 double dot is equal to, I have n2 over n1, and I have tau 1 here. Sorry for the pen, which is making a lot of noise. So I have n2 over n1 times tau 1 here. I have put the right hand side here, minus b times theta 2 dot minus k times theta 2. Okay? So now the only thing that I have to do is to convert these theta 2s into theta 1s. Okay? And in order to be able to do that, I will try to substitute here these variables into here. So I see from this equation that theta 1 is equal to n2 over n1 times theta 2. Okay? So what about the derivatives? I have derivatives here. Okay? Theta 2 dot and theta 2 here. I can convert theta 2 into theta 1 by multiplying with n2 over n1 here, this variable. But you see here I need to convert these derivatives and the second order derivatives as well. What should I do in that case? It is easy to see this actually. If I look at this equation, if I take the time derivative of both sides, this gear ratio is actually constant with respect to time. That means that this is not going to be affected by the derivative at all. The only thing that is going to be changing is theta 1 and theta 2. So if I take the time derivative of both sides, I get theta 1 dot is equal to n2 over n1 theta 2 dot. And if I take the second derivative, it's going to be theta 1 double dot is equal to n2 over n1 theta 2 double dot. Okay? So here I use the fact that this gear ratio is constant with respect to time. The only variables here changing with respect to time can be these theta variables. Okay? That is why they are the only variables that are affected by the derivative operation. So now my task is using these equations to convert all of the theta 2's there into theta 1. Okay? So what I could have done here is to substitute this right hand side and with the derivatives into theta 2 in that equation. Here I don't like to do it in that way. Instead of that, what I'm going to do is I'm going to multiply both sides of this equation with n2 over n1. When I multiply both sides of this equation with n2 over n1, you see that this is going to turn into theta 1 double dot, this is going to turn into theta 1 dot, and this is going to turn into theta 1. Okay? And this is going to be multiplied once more by n2 over n1. That is going to give my differential equation. So I have j times, multiply this equation from the left by n2 over n1, and this is going to turn this theta 2 into theta 1 double dot. Okay? That is equal to, I'm multiplying the right hand side as well with n2 over n1, which is going to give me n2 over n1 square here. There is this still tau 1 minus, still multiplying, b times theta 1 dot minus k times theta 1. Okay? So this is my differential equation representation, which relates the input to the output of this system. So that completes the first part of the question. Let us look at the second part. It's a transfer function representation. Transfer function representation is a Laplace domain representation. And I know that g of s, the thing that we call as the transfer function, is the ratio of the Laplace transform of the output to that of input. All right? And in this case, the output is theta 1. So I'm going to write here capital theta 1 of s divided by the Laplace transform of the input, tau 1. I don't know what the capital of the letter tau 1, so I'm going to write something like t here. It is going to be this strange t1 of s. Okay? Now, in order to be able to calculate that, I will pass this differential equation into Laplace domain. Let us do that. And while assuming zero initial conditions, so a derivative is just multiplication by s, and second derivative is multiplication by s squared, etc. So I have j times s squared. I will multiply it with capital theta 1 of s, but let us keep this like this, and try to take care of the other terms. I have this one is minus b s theta 1 of s. This is going to go to the other side, plus b times s, plus this is going to go to the other side. This is k times capital theta 1 of s. This is k times capital theta 1 of s. That is equal to, I will have n2 over n1 square times capital tau 1 of s. All right? So now all I have to do is to calculate this ratio here. And if I do that, you would see that g of s is given as, I would have n2 over n1 square divided by js square plus bs plus k. This is my transfer function representation. And as soon as I find the transfer function, I can ask you, what is the order of this system? I could have asked the same question here with the differential equation as well. And the answers to both questions will be the same, and the answer is 2. This is a second order system, and therefore when I try to find a state space representation for this system, I need to use two state variables. So this completes the transfer function part, and let us find the state space representation. If you have watched the earlier lectures, this is not going to be difficult. When you have a differential equation in this form, the obvious variables that we choose to represent this differential equation in the state space form are theta 1 and theta 1 dot. So we choose here the variables theta 1 and theta 1 dot. Now let us find the state space representation. X dot is equal to the A matrix times X plus BU, and Y is C times X plus D times U. Let us find the first row of A and B here. X dot here is going to give me theta 1 dot. Theta 1 dot is one of the state variables. It's the second state variable. So I will put a 0, 1 here, and there is no input in that equation. And remember, the input means here is tau 1, and this is the input. And the output means that is the variable theta 1. Okay? So the second equation is going to come from the differential equation. Theta 1 dot here is going to give me theta 1 double dot. I need to write theta 1 double dot in terms of theta 1 dot, and the input tau 1. And that is what our differential equation is actually doing there. Okay? So I have the coefficient of theta 1 on the right is going to be minus k over j. Coefficient of theta 1 dot is minus b over j. And the coefficient of tau 1, which is the input, is going to be n2 over n1 square times 1 over j. All right? This completes the A and B matrices, and the C is going to be is going to be obtained by relating theta 1, the output, to the state, which is the first state variable. So I will put here 1, 0, and 0 here. And this actually completes this example, finding all of the representations that we can find. So here this actually completes my exposition of rotational mechanical systems. When we see the DC motor, we're going to see still more of these examples. That is why I'm going to solve here only a single example. So now I'm going to start with the block diagrams and their simplification, which is going to be the second part of this lecture. So let us start with block diagrams. And their simplification. So So I'm not continuing here with the DC motor because when we try to obtain mathematical models, especially the transfer functions for systems involving DC motor, we are going to be using the concepts of block diagrams and their simplification a lot. These are going to make things easier when we try to deal with more complicated systems, especially systems with DC motors. So here the first thing that we have to know is this. Suppose that I have a system with transfer function g of s, and this is the input u of t and the output y of t. So suppose that we know the transfer function, we know what g of s is. Then what I would have to understand is that what is the Laplace transform of the output when I know the transfer function and the Laplace transform of the input? The answer is going to be quite easy. So this is g of s, and I know that it is the ratio of the Laplace transforms of the output to the input. And as a result of this expression, the Laplace transform of the output of the system is always going to be the transfer function of the system times the Laplace transform of the input. It's the same equation as you see here. Okay? So when you have the transfer function of the system, then if you know the Laplace transform of the input, then you know what the Laplace transform of the output should be. It is going to be the multiplication of the transfer function with the Laplace transform of the input. So then we are going to get more and more complicated systems. The first system is going to be the serial connection of systems. And this is going to be looking like this. I will have two systems represented by two transfer functions, g1 of s and g2 of s. And I'm going to be connecting these two systems like this. I will connect the output of the first system to the input of the second system. And then I will get another output here. Okay? So this is my input, u of t. This is the output of the first system, and this is the output of the second system. When I have such a connection, this is called the serial connection of two systems. We are going to be talking about what the overall system is. Okay? So I'm going to be asking the following question. Suppose that I would like to represent this system with a single block. Okay? This single block would be looking, maybe I didn't draw it in a nice way. I should have drawn it like this. Sorry. So this y2 is remaining there. I am actually cutting this block here. So suppose that I would like to think about these two systems as a connected system, and I am wondering about what the transfer function of the overall system that I get by connecting these two systems in this topology. Okay? Let us try to derive that. So I know that here the Laplace transform of this input is u of s. What is going to be the Laplace transform of y1? It is going to be the transfer function times the input u of s. So it is g1 of s, u of s here. The Laplace transform of y1 is going to be this. And what about the Laplace transform of this y2 of t? It is going to be y2 of s, and what is that going to be? It is going to be the transfer function times the Laplace transform of the input. Transfer function times the Laplace transform of the input. But I have just calculated the Laplace transform of the input here, and that is, which is y1. It is g1 times u of s. So the Laplace transform of y2 is going to be g2 times transfer function times the Laplace transform of the input, g1 of s, times u of s. Okay? So I see here that I have these expressions for this connected system. So then what can you say for the overall transfer function of the overall system, this connection? What is this overall connection equivalent to in terms of the transfer function? We are going to obtain the overall system. It is going to be the equivalent transfer function of the system. We know that transfer function from u to y2 is going to be transfer function, the Laplace transform of the output divided by the Laplace transform of the input. Okay? What do you think this ratio is in this case? This is y2 of s is given like this, and in this case, if I take that ratio, this is going to give me the multiplication of g1 of s times g2 of s. Okay? So when you have a serial connection of two systems, then the overall transfer function of that connection from this input to the final output here is going to have the transfer function g1 times g2. Okay? When you connect the systems by giving the output of the first one to the input of the second one, then the transfer function of the overall system is going to be the multiplication of these two transfer functions. So now let us come to the second part. It is parallel connection of systems. In this case, I'm considering such a topology. So I have a common input, u of t, given to these systems. I have g1 of s as the first transfer function, and I have g2 of s. I'm giving the same input to both of the systems here. Okay? And then I'm summing their outputs. So the topology is looking like this, and this is my y of t. So when we have such a connection, this is a parallel connection of two systems, and now I would like to think of it as a single block. Okay? With this input and this output. What is the overall transfer function of such an overall system here? This is actually probably easier than the first one. So in this case, it's going to be summation. Okay? So what is the Laplace transform of this output? It is going to be the transfer function times the Laplace transform of the input. Input Laplace transform is both u of s for both of these systems. So this signal has the Laplace transform g1 of s, u of s. This signal has the Laplace transform g2 of s, u of s. And then I'm summing these, which means just the summation of these two signals, and that is going to be g1 of s, u of s, plus g2 of s, u of s. But I can take u of s parentheses here, g1 of s plus g2 of s in parentheses times u of s. So the overall transfer, this is my y of s here. This is y of s. So here, if I want to obtain the overall transfer function of this system, overall transfer function of this block here, it is going to be ratio of the output Laplace transform to the input Laplace transform. So since this is y of s, this is my y of s here. And if I divide y of s by u of s, I get g1 of s plus g2 of s. So when we have a parallel connection of systems, the overall transfer function can be found by summing the transfer functions, individual transfer functions. When we have a serial connection of systems, the overall transfer function can be found by multiplying the transfer functions. So these were the easier connections. Now we're going to see probably the most common connection that we will encounter in this course, and that is called the feedback loop. It is going to be looking like this. I will have a system here. This is going to be called G of S. And I will have a feedback path. This is h of s. So I give the input here, that is u of t, and this is my output, y of t. Okay? And we have a connection in this form. So again, we are going to be wondering what the overall transfer function of such a system would be. Okay? I'm going to consider this as a single block. It is the overall system, and we're going to be wondering what the overall transfer function is. So here, this part of the loop here, there is a loop here, as you see. There is a signal is going from here to the output, but along the way, a branch is separating out and it's going back to the input here. That is called the feedback loop. All right? And this loop has two parts. This is the first part is this. This is called the forward path. And the second part of the loop is this. This part is called the feedback path. Okay? And we are wondering again about the overall transfer function of such a connection. So here, most of the times, we are going to be calling the signal here as E of t. This is called the error signal here. We are subtracting from u of t the signal coming from y of t passing through h of s. So we apply a subtraction here, and this difference is called the error signal, that is E of t. And we would like to calculate the overall transfer function of such system. So here, this is a loop, so we are going to call the transfer function that we get for this overall system to be the closed loop transfer function. I am going to be calling it as GCL, denoting closed loop here. GCL of S is going to be the ratio of the output of the block to the input of the block, their Laplace transforms. So y of s over u of s. We are wondering about this overall transfer function. What is the closed loop transfer function which represents all of this material here from u to y of t? Okay? In order to be able to find the overall transfer function here, I'm going to be writing all of the equations that are coming from such a system. So now let us try to write them. The first thing that I'm going to write is E of s. E of s is the subtraction of two signals. The first signal is u of t. Its Laplace transform is u of s. Minus, I'm subtracting this signal from E of t. From u of t, okay? U minus this signal is giving me E. So E is u minus this signal. What is the Laplace transform of this signal? I see that this system, this is called the feedback system. This feedback system, feedback path system, is taking y as the output, and it's giving this signal as the y as the input, and it's giving this signal as the output. Remember, the Laplace transform of the output of a system is the transfer function times the Laplace transform of its input. Okay? Laplace transform of its input is y of s times h of s is going to be the Laplace transform of this signal. So it is going to be h of s, y of s here. All right? So the Laplace transform of this signal is h times y of s. Transfer function times the input, Laplace transform of the input of that system. So this is my first equation. It relates it relates the signal E with the input signal and the output signal. Now I'm also going to be writing what y of s is. Y of s is, so this signal is the output of this system. And I have the input of this system as E of t. So what should be the Laplace transform of the output signal? It is y of s is the transfer function g of s times the Laplace transform of the input, which is nothing but E of s. So these are the two equations that I can obtain for this system, and then these are going to give me the closed loop transfer function of this loop. All right? So what should I do in order to be able to find this transfer function? We see that I need to express y only in terms of the variables in u. I need to express y only in terms of u in order to be able to find this transfer function. So here, in these two equations, I have y, I have u, but I have also some extra variable, which is e of s. So if I cancel from these two equations the signal e of s, then I'm going to get my equation that I can use to obtain the transfer function here. Okay, so that is what I'm going to do. So I'm going to, instead of this e of s, I'm going to use the first equation, and I will get an equation only in terms of y and u here. So y of s, this is my second equation, g of s times e of s. Instead of e of s, I will use the first equation. So I have u of s minus h of s, y of s. Okay? So you see that in this equation there is no other variable than y and u here. All right? All the other variables, this g and h, they are parameters. Okay? The variables, the signals are u and y. These g and h, they are representing parameters of the system. So in this equation there are only two signals, y and u. So now what do I have to do? I need to express y in terms of u only. If I expand this, if I distribute this multiplication over this subtraction here, it's going to give me g of s u of s minus g of s h of s y of s. Okay? And then I will take all y of s terms on one side. It is 1 plus g of s h of s in parentheses times y of s is g of s u of s. Now you can actually obtain this ratio. What is y over u? Y over u is g over this term. Okay? That is going to give us the closed loop transfer function. So G closed loop is going to be y of s over u of s, and this is equal to, I can write from there, g of s divided by 1 plus g of s h of s. Okay? I will call this equation here as the feedback rule. Okay? So let me explain what the terms are. G is the transfer function in the forward path. Okay? G is transfer function in the forward path divided by 1 plus everything in the loop. G and G times H is in the loop. Everything in the loop is G times H. So the feedback rule tells us that if I have a feedback connection in this manner, the overall transfer function of such a system would be the forward path transfer function, G of s, divided by 1 plus everything in the loop, G times H. Multiplication of both forward path and feedback path transfer functions. So this is my feedback rule. Sometimes, although it's rare, we have the following system. Instead of a negative feedback here, we have a positive feedback system in this manner. So I have G of s and H of s the same. But instead of the negative feedback here, we have a positive feedback here. In that case, we might be interested in, again, what the overall transfer function is. So this is my u of t, and this is y of t, and we are again considering this system as a single block, and we are asking the question, what is the overall transfer function? What is the closed loop transfer function? Do you think you can extract it yourself from this analysis? What would it be? So here, what is going to change in these two equations? Here, E of s is the subtraction of this signal from u In the other case, I will have an addition instead of a subtraction. So this minus sign is going to turn into a plus, all right? And then this is going to turn into a plus. This is going to turn into a plus. So this is going to turn into a minus, and you have your ratio. So in this case, G closed loop of S would be G of S, forward path transfer function, divided by 1 minus everything in the loop, G of S, H of S. Okay? This is the positive feedback. And this is our formula for negative feedback. Okay. So in general, the blocks that we are going to consider will not be really this simple. So these are really blocks, connections, or block diagrams that can be considered simple. In general, we are going to have much more complicated block diagrams, and we are going to need to find their overall transfer function. So now we are going to start with an example, and this example is going to be an example where none of these rules that we have seen will be applicable. Okay? So in the example, we won't be able to apply this feedback rule immediately to find the overall transfer function. Or we won't be able to apply the multiplication rule immediately. We won't be able to apply the parallel connection rule immediately. So we will see how to make modifications on a block diagram to be able to calculate the overall transfer function using these rules, these intermediate rules. So let us call this an example. The example is looking like this. I have an addition here with negative feedback. And I have G1 here. Here I need to write G1 of S, but I won't. You need to know that there is an S there which is neglected in this writing for the sake of brevity. So I have G2 here, and I have G3. So this is my Y, and this is my U. But unfortunately, it's not only these blocks. So I have here a feedback path, which is H2, and it's going into this feedback path. And finally, I have a path coming from here, and it's going into this. So I have H1 here going like this. The task is the same. Find the overall transfer function of the system. Okay? In terms of these G1, G2, G3, H1, and H2. In this case, unfortunately, none of the rules that we have seen is applicable. Okay? Here I can try to multiply G1 and G2 and put this as a single block here, but it is not possible because of this branching, because of this branch here. Here I cannot just multiply G1 and G2 because there is a summation in between, right? Or a subtraction in between. Similarly, I can try to use a feedback rule here, but you see here that there is a branch coming out of in the middle of the feedback loop. So I cannot use feedback rule on this loop here. Or I cannot use the feedback rule for this loop. There is a forward path, there is a feedback path, but right in the middle there is just a summation here. So I cannot handle that summation in the feedback rule. So now we are going to see how to obtain the overall transfer function of such a interesting connection. So in this case, the first method is going to be the algebraic method. And this first method will consist of writing all of the equations coming from this system. Okay? Write all equations coming from this system and then try to find y over u. Y of s over u of s, which is the overall transfer function of this system. Okay? That is the first method. So in order to be able to do that, I will give some names to some intermediate variables here. I will call this variable as E1 and I will call this variable as E2. Let us now try to write all of the equations that are coming from this system. I will first write the equation for E1. E1 is, this is the difference between u and this signal. Okay? It is u minus, there is a minus sign here, minus this signal coming from here and going into that minus sign. What is the Laplace transform of that signal? This signal is the output of the H2 system. So the output of the H2 system, its Laplace transform, is going to be the transfer function H2 times the Laplace transform of this signal. And what is the Laplace transform of that signal? This signal is the output of G2 and the input is E2 here. So the Laplace transform here is nothing but G2 times E2. Okay? Why is that? This point here is the Laplace transform of the output of G2. And the Laplace transform of the output of G2 is going to be the transfer function G2 times the Laplace transform of the input. So this point is G2 E2 and this is going to the input of H2. Then what is the Laplace transform of this output? It is going to be H2, G2 and E2. Okay? So then what should I subtract from u here? I'm going to write this as G2, H2, E2. I can change their places, it really doesn't matter. So here I have this equation for E1. Okay? Let us write equation for E2. E2 is this signal minus this signal. Okay? And what is the Laplace transform of this signal? This is the output of G1 system. So it is Laplace transform is transfer function times the input Laplace transform. So it is G1 times E1. This is the plus sign minus, I need to write the Laplace transform of this signal. This is the output of H1 system, and H1 is taking y as the input, and its output is the signal that I want. It is Laplace transform is going to be H1 times the Laplace transform of y. So it is H1 times Laplace transform of y. Okay? This is the equation for E2. And finally, what I have to do is to write the equation for this y here. Y is equal to, y is the output of the G3 system, and its input is G2, E2, and there is also the transfer function G3, so y of s is going to be this one. G2, G3 times E2. Okay? So I will just have these three equations coming from this system. And these are relating all of the variables to each other in this system. And by just using these equations, I can try to extract the overall transfer function of this system. What do I mean by the overall transfer function? Obviously, the ratio of the overall output to the overall input. Okay? So I'm trying to calculate G of s here, the ratio of Laplace transforms of the output to the input. So I want to calculate y of s over u of s. But you see here, in these equations, I have many more, not many more. I have just two extra variables that I need to get rid of. All right? So I need to get rid of here get rid of E1 and E2 from these equations. Okay? So here is what I'm going to do. So this is always a problem. When you get these equations, you have to come up with a strategy to cancel this E1 and E2 from these equations. Okay? The first thing that I'm going to do is I'm going to get rid of E1 by substituting it from the first equation into the second equation. In general, the strategy that you need to apply can be much more complicated if you have a more complicated block diagram. So let me write the second equation. The second equation is E2 is equal to G1 times E1. Instead of E1, I take the right-hand side of the first equation. It is U minus G2 H2 E2, and I have the rest of the second equation here, minus H1Y. All right? So you see that this equation is only related to E2 and Y. Okay? So I can actually try to extract E2 in terms of the input and the Y, output Y here. The input and the output are the only variables that I want to remain in this equation. I want them to remain in this equation, and I want to get rid of E1 and E2. And by doing that substitution there, I got rid of the E1 variable. So this is going to be E2 is equal to G1U minus G1G2 H2 E2 minus H1Y here. Okay? Now I will collect all of the E2 variables on the same side. 1 plus G1 G2 H2 times E2 is equal to G1U minus H1Y. Now the only thing that I have to do is a division. E2 is G1U minus H1Y divided by 1 plus G1 G2 H2. Okay? So now this represents E2 in terms of the input and the output. Now I come to the last equation which I have not used. If I substitute E2 in this equation, then I'm going to be in a better position, because then I will get rid of E2 variable as well. Let us do that. So Y is equal to G2 times G3, I will have these equations, G2, G3 times G1U minus H1Y divided by 1 plus G1, G2, H2 here. Okay? I need to erase this. So now I have to make some algebra in order to be able to obtain Y only in terms of U and some parameters. Okay? So I will first take this part to the other part. So it is 1 plus G1 G2 H2 times Y is equal to, let me multiply, distribute that multiplication, G1 G2 G3 times U minus I have G2 G3 H1 Y. So now I can collect all of the Y terms on one side. So here I have 1 plus G1 G2 H2 plus G2 G3 H1 Y is equal to G1 G2 G3 U. Now the only thing remaining is to calculate that ratio, Y over U. Okay? And from this I see that Y over U is going to be this over this term, this complicated term. So G of S, the final expression that I have to find here is just this. G2, G3, H1. So this is the answer of this question. But you see that this was a purely algebraic method here. I have only used algebra here and cancelled some of the variables, and then we have obtained our final result. So this was the first method. This is the algebraic method. So the second and the third methods would be some graphical methods. And what I'm going to do is here to modify that system such that I can apply the rules that we have seen so far. I'm going to be modifying this system such that I can use the rules, serial connection, parallel connection, and the feedback loop connections. Okay? So the first thing that I'm going to do is, how can I modify this system such that I can use my feedback rule? I can do this in two ways. So what if this branch was not here, but it was here? Okay? If this branch was not here, but it was here, then there would be a small feedback loop here. Okay? And I can replace that small feedback loop with its equivalent transfer function, and then I will have a larger feedback loop here. Okay? Then I can again use the feedback rule there. So the first thing that I'm going to try is, I'm going to try to take this branch here, this is coming from here to there, from here to here. Okay? Here really it doesn't matter if I take it here or here. Okay? These are always the same signal. This is like a voltage in a circuit. These are always the same system. So when I take it here, it also means that it is here as well. All right? So let me try to do it. Unfortunately, I will have to draw almost all parts of this system again. I'm sorry. So G1 is here. I have G2 and G3. Now, instead of taking that system, I will take this branch out, the upper branch. It is going to be H2. It's going to go here. Now, instead of taking this branch out from here, I will take it out from here. Okay? So this is going to be H1 here, like this. So this is quite easy, as you see. Or is it? So when I make such a modification, when I take this branch from here to here, do you think these two systems would still be the same system? If I want to calculate the overall transfer function of this system, then when I make a modification on this system, I need to make sure that both systems are the same. Because I'm going to calculate the overall transfer function of that system. If these two systems are not the same, then it's going to be meaningless. The result that I find will not be related to the original system in any way. So here, when I try to make a modification, actually I made a mistake. Okay? I didn't do it correctly. When I try to modify, when I try to take this branch from here to here, I need to make a further modification on this system. And what should be that modification? We have to think about it. I need to make sure that all signals here are the same as all signals, all the corresponding signals in that original system. Okay? So here I really do not see any change. So this difference is going through G1, and it's going to do summation. So it's going to G2, it's going to G3, and it's going to the output. Here, I really do not see any changes. And this signal is again going back to the input, going through H2. But obviously, there is a change here in the system. Okay? So now, what is the signal here going through H1? Here, the signal going to the H1 is coming out from G2, and then it's going directly to H1. Okay? Here in the modified system, the signal output of G2 is directly going to H1. What was that output doing in the original system? In the original system, this signal was going to H1 by first passing through G3 and then going to H1. Okay? But here, the same signal is going to H1 directly, which makes these two systems different actually. Okay? So we don't want such a difference between the systems when we make such a modification. So what I have to do again here is that I need to make sure that this signal goes to H1 goes to H1 after passing through G3. Okay? So this signal should go to H1 after passing through G3. So here, what I can do here is putting a G3 here. Okay? If I put here a G3 block, then it's going to make sure that they are the same. But here, instead of putting that G3 here, I can put here it as well. Okay? So this signal goes, I can make the multiplication first with G3 and then with H1. So this signal will be the same as this signal in the previous system, in the original system. Okay? So these two systems now would be equivalent to each other. How did I do it? I can put here a G3 block in order to make the system the same, make the signal the same as the corresponding signal in the original system. But that G3 here it would not really matter if I put it in front of H1 here, because when this signal first enters here, it really doesn't matter which one I'm multiplying it with first. I can first multiply it with G3 and then H1, it would give me the same signal if I multiply it first with H1 then G3. So therefore, this modification, this addition here would make these systems equivalent in terms of the input-output sense. So now I can actually apply the rules that I have found before. So you see that when I make this modification, when I make sure that both of the systems are now the same, here there is a smaller feedback loop that you see here. Okay? So this is a smaller feedback loop inside a larger feedback loop. And we see that we really do not have any more branching outs in the middle of the feedback loop or summations in the middle of feedback loop. Okay? Now I can actually apply my feedback rule to replace this small feedback loop with its equivalent. Let us try to do that. So I will put here one minus here and G1. Now, instead of this smaller feedback loop, I will write its equivalent transfer function here. Okay? What is going to be that equivalent transfer function? It is going to be the forward path transfer function, G2, divided by 1 plus. If there is a minus sign, then there is a plus here. Everything in the loop. Okay? G2, G3, H1. Okay? This is equivalent to this feedback loop here. It's G2 forward path transfer function divided by 1 plus, because this is a negative feedback, everything in the loop, G2, G3, H1. It really doesn't matter in which order you are multiplying this. Okay? So these are commutative or associative, you can say. So I have here this G3, and I would have a branch here still remaining going out from here, and then that is going to be H1. Okay? Now what did we obtain? Here we replaced this complicated part with a single block, and then the remaining thing is another feedback loop. Okay? So this remaining system here, this system from here to there, it is just a large feedback loop. Okay? The first thing that I'm going to do is that I can combine these two blocks. How can I combine it? This is a serial connection of two blocks. Okay? This is just going to be the multiplication. Alright? So the equivalent transfer function of these two blocks will be G1, G2 divided by 1 plus G2, G3, H1. Okay? This is the forward path transfer function, and the feedback path transfer function is h1. So this here I can use again a feedback rule. Let us try to write the overall transfer function of that block. So in order to be able to do that, I will raise this. So here, remember, I will think that these are already combined. So what about the overall transfer function of this larger feedback loop? It is going to be the forward path transfer function. This part is the forward path transfer function. G1, G2 divided by 1 plus G2, G3, H1 divided by 1 plus. Because of this negative feedback, I need to put here a plus, everything in the loop. Multiply everything in the loop. So I have G1, G2, H1 divided by 1 plus G2, G3, H1. Okay? This is this block. It is the feedback loop. And I have one more G3 connected to it. Okay? And there is the input here, U. So now I can make this, apply some algebra here, and this algebra is going to give us the following. So this is going to be, I will have this G1, G2 divided by 1 plus, I would have G2, G3, H1, G2, G3, H1 plus G1, G2, and H1 here. Maybe I made a mistake somewhere here. Yes, this mistake is here. So this was H2, but I have written H1 here. I'm really sorry about this. So here, while passing through to here, I need to replace this thing with H2. Okay, so this thing is G1, G2, H2 here. So this is my single block that is taking the input U, and I will have also this G3 at the end, and these two are going to be multiplied. So I will have G3 here, and this is Y. So this is my overall transfer function here. Okay? It should be the same transfer function that we found with the first method. Okay? So if you check those, you need to see the connection between these two. Let me check. G2, G3, H1, G1, G2, H2. Yes, that is correct. So now I have done this with the graphical method. Now I will try to apply another graphical method here. Maybe I can. Sorry, I will try to draw it once more. So these parts can remain. Okay. So this is going to be our third method. So we have the same blocks as before, and the summation here. Now remember the second method. I have taken this branching here from here to here. And then this gave me a smaller feedback loop here, okay? And then that smaller feedback loop became a part of a larger feedback loop, and then we have calculated the overall transfer function like this. Now, instead of taking this branch from here to here, what I can do here is take this branch, the upper branch, from here to the end of the system, okay? So now that is what I'm going to do. I'm not going to do anything with the lower branching here. So that is H1 still. This part is the same. Now instead of branching out in the middle of these two systems, I will take that branching out from here. Okay? This is going to be H2 here, like this. So I can here again ask the same question. Are these two systems the same? And the answer is going to be unfortunately no. So when I take this branching from here to here, I make a mistake somewhere. So I need to apply some compensation on this new system such that these two systems become equivalent again. Now let me look at the signal here. This signal in this system, in this modified system, is coming from H2, and the input of H2 is coming from Y. Okay? That is in the new system. But what is, and this Y is coming from G3. All right? In the earlier system, in the original system, this signal was going to H2 directly. This signal was going to H2 directly in the original system. But in the new system, this signal is first going through G3, and then it's going to H2. Okay? This is the difference between these two systems. Here in the original system, this signal, the signal in the middle of G2 and G3, is going to H2 directly. But in the new system that I have drawn, this signal is first going through G3 and then it's going to H2. So here, this signal has some extra components in it coming from G3. Okay? So what should I do here as a compensation to make these two systems equivalent? And the answer is that if this system, if this signal has some extra components coming from G3 here, I can try to cancel G3 when this signal comes to here. So what I'm going to do is that I'm going to divide here this transfer function with G3. Then these two systems would be equivalent. Why? Because this signal is then going to pass through G3 and it's going to go here. There is a division with G3 here which is going to cancel the effect of this block, and then this signal is going to go directly to H2. All right? So now these two systems are actually equivalent to each other. So now let us try to find this new compensated system which should give us the same result. Here you see a smaller feedback loop. So if you just try to carry out some exercise from your books, actually I will also try to give you a homework about this. You need to try to see feedback loops everywhere you look here. And here I see a feedback loop here, and I can calculate its equivalent transfer function. Let us calculate it is equivalent transfer function in this case. What is it going to be? Forward path transfer function G2 G3 divided by 1 plus, because of this minus sign, everything in the loop, G2 G3 H1. Okay? This complicated block here turns into this single transfer function. Okay? Then imagine that you replace this block, this complicated block, with this single transfer function. In that case, you will see also a very, very large feedback loop going from here and then coming back from here. Okay? Now, what we are going to do is to calculate the overall transfer function of that larger loop. That is going to be my G of S here. Let me put it a little bit lower. So G of S is going to be the forward path transfer function of that larger loop. It is going to be G1 times this thing, forward path transfer function, G1 times what is equivalent to this feedback loop. It is G1 times this, G2 over 1 plus G2 G3 H1 divided by 1 plus, because of this minus sign. If there were a plus sign here, then I would have put minus sign here. Everything in the loop. Okay? Everything in the loop. So I have this thing again, G1, G2, divided by 1 plus G2, G3, H1 here. And here, what I'm going to do is that I will, sorry, there is a mistake here. G1, G2, G3, G1, G2, G3. Sorry for this mistake. I was wondering what I was going to do here. So here, it is this one times this feedback loop. G1 times this thing. G1, G2, G3 divided by this. 1 plus everything in the loop. Or I have already these two, times H2 over G3. H2 over G3. And this G3 is going to cancel this one. I was expecting for this cancellation. That is why I was surprised that it didn't cancel. So this is equal to, and then what I'm going to do is equate the denominators and try to write what we get as the result here. So here I have this thing like this. And then let us equate the denominators here. I will get G of S is equal to G1, G2, G3 divided by, when I equate the denominators here, the denominators are going to cancel with the numerator, all right? And then I will get 1 plus this thing, 1 plus G2, G3, H1 plus G1, G2 times H2. G1, G2, H2. And this is going to give me the overall transfer function. Okay? And if you compare this new one with the old one that we have found, they should be the same. Okay? Sorry, I made in this lecture I made really lots of mistakes. I'm sorry for that. So I have studied about this before coming here, but we really do not know. When in a classroom, usually students give feedback so that I correct my mistakes immediately, but here, unfortunately, I don't have that opportunity. I hope you tolerate this. So that is going to be all for this lecture. In the next lecture, we're going to see DC motor, and we're going to see how we can actually use these block diagrams in order to be able to take advantage of their simplicity in calculating the transfer functions with DC motors. That is going to be all for this lecture. Thank you for watching.